Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video, we're going to be talking about context-free parsers and how we can use a library that's part of Scala in order to create parsers for context-free grammars. Now, to help motivate this, so first let's look at the library itself. There is a library, Scala util parsing, and there is a package, the combinator package in here, which has a number of different parsers in it. The one that we're going to use is the Java token parsers because it has some things built into it that will help us do what we want. Now, as an example of where you would want a parser, one of the standard applications for this would be you kind of want to have your own little language built into your program. If people who are working through the textbook, if you happen to be doing something like something that's text-based, the MUD, for example, you might have an interest in coming up with commands that are more complex than just one or two keywords, and using parsers in order to parse out those commands would make sense. You could actually write a parser for, if you find an appropriate grammar for English. These context-free grammars are used in lots of other places too, and as an example of this, I've pulled up a page. This is for Antler, which is it's a compiler tool that's written in Java, and it's for doing parsing. And part of going along with this is people have uploaded their grammars. So these are context-free grammars for different languages. There's a long list of them here. One of the simpler languages that I like to point to is Ecmascript. You probably know this better as JavaScript. And while it's a fairly simple language in many ways, in some ways the parser is fairly simple, you'll see that the context-free grammar for it is still reasonably long. This includes the ability to do ifs and function calls and their try and catch and all the types of things that exist in that language. I want to focus on just a small portion of this that has things like additive expressions, multiplicative expressions, unary expressions, prefix expressions, and then primary expressions. And this is how they express the ability to write. So, for example, if I do 3 plus 5 times 2, that would be under an additive expression, because additive expressions are built out of multiplicative expressions followed by either a plus or a minus and another multiplicative expression. There are details to this grammar here that we don't care about. Some things should look familiar because, for example, this star here is the same as in a regular expression. It means that the stuff in parentheses before it can happen 0 or more times. So an additive expression could just be a multiplicative expression, or it could be a multiplicative expression followed by 0 or more of these here. And so you can go through and figure out exactly what that means, because then a multiplicative expression has a unary expression separated by one of those operators from other unary expressions, and then the unary expressions have their unary operators that they allow in JavaScript, some of which, for example, you might not be used to these as unary. In the C family languages, plus plus and minus minus are unary increment and decrement. And this can have a postfix expression, which those appear again, and then you eventually get down to the primary expressions, which can be things like variable literals, so they can be variable literals or numeric literals, either any of these things. So this gives you some idea of where a grammar can be useful. This is how we define our programming languages in computer science, is actually using these grammars. Now, what I want to do is I don't want to have a full language at this point. We're not going to try to write a parser for the entirety of, for example, the JavaScript. Instead, I want to write a little class, a parser formula. Now, this is going to be very similar to one of the examples that we did with our when we were talking about recursion in a recent chapter, where we used recursion and a divide and conquer approach to parse a formula, and then in the trees chapter we took that parser and we extended it so that it would build a tree for us. Here I just want to use the parsers, kind of a simpler example in Scala of what we just saw as an option in the antler parser. So I want to start off, we're going to make formulas here, and these are going to be very simple formulas. I'm going to start writing in a terminology that's similar to what, for example, it's not exactly the antler terminology, it's not exactly what we're going to wind up putting in Scala. It should be something that's fairly easy for you to read to see that this is a context-free grammar. And we're going to say that a formula is equal to a term, and I'm going to use curly braces to denote things that can happen 0 or more times. Actually, maybe I'll just, I'll use curly braces. This is following along with the book. The antler notation would have been parentheses and a star, and in some ways that is probably closer to the regular expressions that we just saw. And then inside of here, you can either have a plus sign or you can have a minus sign, and then that is followed by another term. Okay, so that's the possibilities for a formula. Of course, the formula relies on the definition of a term. And what can a term be? Well, a term can be a factor followed by multiplication or division. Actually, it's an or. I want a pipe here. Or division and another factor. Okay, and remember, the curly braces mean 0 or more times. So this could be 3 times 5 divided by 7, however many we want in there. And then, of course, the term depends upon a factor. So what is a factor? Well, a factor is defined as a floating point number, or it is parentheses wrapped around a form. So note that this winds up being recursive and goes back up to the top of the definition here. And this is a simple context-free grammar that represents formulas in the sense, or expressions that involve addition, subtraction, multiplication, and division. And note that it automatically has proper precedence or order of operation here, in that because the plus and the minus bind at this higher level in the grammar, they are actually lower precedence operators. The multiply and divide are kind of more deeply nested in here. And then, of course, anything that's inside of parentheses gets further priority. So what I want to do in this video, now that we've kind of introduced some basic kind of terminologies, I want to convert this over to equivalent Scala parsing code. Okay. Now, when we do this, one of the things that I'm going to do is I'm going to make it so that we extend that Java token parsers that we saw in the libraries there. Okay, and that will give us access to all of the parser things that we want. In our first version of this parser, I'm literally going to take this here, paste it in there, and now I want to change these so that they fit how we're supposed to do this in Scala. It's a fairly simple set of transformations. First, every one of the productions is going to go from just being the definition that was up here to a def. Okay, these are actually going to be written as functions, and these functions return parsers. Right now, we're making these that they are parser of any. Okay, so copy that, paste, paste. Okay, we're getting close. So we make it so that these things are a parser of any, and what they return is going to be this, but we need to change up the syntax a little bit. So the Java tokens, the parsers themselves, have define some operators on them. So for example, instead of putting things separated by a space, you use a tilde. For repeating, we use a function called rep. And then inside of here, we want another tilde, whoops, that's not a tilde, to separate things. And now that's in the proper format for Scala. So tilde, rep, and tilde in there. So the tilde is used to adjoin adjacent things, things that should go right next to each other. And our only problem here is that instead of just having spaces, these need to be tilde separated. And boom, there we go. So this has taken what was written kind of in a general, almost a theoretical form of how we would define a grammar for a context-free grammar, and converts it into Scala-based parsers. So we'll come back to this in the next video, and we'll see how we can utilize this and what